Hello dear student, this is Devang Shah from LG Institute of Engineering and Technology from LG University. Now in this particular chapter in a logic gates boolean functions, we have discussed about the basic logic gates, then universal logic gates NAND and NOR, then exclusive logic gates XOR and XNOR. After that, we also learn about the Boolean algebra, where how we can reduce the Boolean function into a less number of, or how we can represent the Boolean function into a less number of logic gates using the specific algebra, right? Where we learn a different kind of laws like associative law, distributive law, commutative law, and De Morgan's law, and inversion law, identity laws, right? Now, based on that, further we simplify our universal gates NAND and NOR in a broad way. So if I want to call it NAND and NOR gates are the universal gates, I have to give the specific reason in what way I can consider this NAND and NOR gates are the universal gates, right? So the NAND gate and NOR gate can be said to be universal gates since combination of them can be used to accomplish any of the basic operations and can thus produce an inverter, OR gate and AND gate. So the complete digital electronics, or if you want to realize any digital circuit, you must have to use three basic logic gates, or any Boolean function if you want to represent or if you want to implement in part of the digital circuit, you have to realize three basic gates AND, OR and NOT, right? Based on that, see, you can implement those logics, ending logics, ORing logic and NOT logic using the NAND and NOR exclusively. So what I mean to say that using NAND and NOR only you can realize AND gate, OR gate and NOT gate, right? So let us further discuss in that accordance. So if I want to convert or if I want to realize the NOT logic with the help of NAND logic gate, how can I realize it, right? So if you take the NAND gate and how you can realize the NOT gate. So I mean to say that you have to just realize the kind of Boolean functions. So far what we learned about the NAND gate has a two input and NOT gate has a single input. So my first job is to convert two input into a single input. So what I'm going to do, I'm going to apply A and A to both the inputs. So in a way, I have shorted my two inputs of the NAND gate and applied only A. And from that, with the Boolean function of NAND is like, if I'm going to consider a simple general NAND gate with variables A and B, right? My output is y is equal to A dot B whole bar. Now instead of B, if I'm going to take the same input A, so my input becomes A and output is A dot A. You can convert into A as per the Boolean algebra. So A bar, that is what the function of or Boolean function of NOT gate. So by that way, see, you realize how you can convert or how you can realize a Boolean function of NOT gate using the NAND gates only, right? So this is what the functionality or a kind of method behind to convert a NAND gate into a NOT gate, right? So this is what a kind of NAND gate we have used. We have shorted the input, two inputs, and we have applied a single A, and from that your output would be A bar. So you can see from the truth table where you can realize the NOT gate. Where you apply 0, you'll have a output is 1. When you apply 1, you have a output is 0, right? Same way you can also realize the AND logic with the help of NAND, right? So NAND is what? Is nothing but the AND plus NOT, right? And after that, you just need to connect the NOT. So it's nothing but using the inverse law, it becomes AND bar of bar, it becomes the AND gate, right? So here you just need to do like, you first put the NAND gate and then you put the not function with the help of NAND, see, you can realize the AND gate. You can see this a kind of digital logic gate that having only NAND gate but realize the truth table and boolean function of AND gate. That's what we have to do. So you can see the first gate is a NAND gate having the two inputs A and B. So output is A dot B bar, and after that I just put the not function using the NAND. So A dot bar of bar or A dot complement of complement, I'll have the boolean function is A dot B. So A dot B is nothing but the boolean function of AND gate. By that way, see, you can realize the AND boolean function using the NAND gate, using the NAND gate, right? So check the truth table where A, B, 0, 0, 0, 1, 1, 0 and 1, 1. As such, the AND is only when both the inputs are 1, 1. You can realize the AND gate 1, right? So this is how you can convert AND gate, how you can make AND gate using NAND gates only. Same way, the one more basic gate is defined as a OR gate, and you have to realize the OR gate using the NAND gate, right? So how can you do this? Just think for a 2 second. Yes, NAND is AND plus not, right? Here you have to realize the OR. So ultimately, your terminology is not then NAND, not then NAND. So it's like, you can see this after A and see A and B, two inputs are given to NOT gate, and that NOT gate is again connected with the NAND gate. See, you can realize a kind of A plus B. So here you applied A and B. Now I have developed here, you can see there is a implementation of NOT using the NAND. So output is A bar and B bar, and that A bar and B bar, if you apply to NAND gate, it becomes A bar dot B bar of whole bar. So finally, if you apply the De Morgan's law, A bar of bar plus B bar of bar, so ultimately your output is A plus B. So A bar of bar plus B bar of bar, so output is A plus B, and that A plus B is nothing but the Boolean function of OR gate. So by that way, you can also realize OR gate with the help of NAND gate. That's why NAND gate is called a universal gate, right? Wait, here again we have to convert XOR gate into XOR gate from NAND gates only, as well as the NOR gate from NAND gates only, right? So this is just you can see you can see the truth table here, where that is realization of OR gate. Same way here you can also explore, or you can also make the XOR gate using the NAND gate. You can check the output, see, where you first take the NAND gate, apply A and B, you can realize A dot B bar, and that is equal to A bar plus B bar. Then straight away you can apply this, and from that you can be able to realize the function A bar into B plus A into B bar. So that is nothing but the kind of realization of NAND gate, sorry, realization of XOR gate using the NAND gate, right? So same, if you apply and you can check the Boolean function, where you can check the truth table, and that nothing but the realization of XOR gate using the NAND gate, right? The same thing if you implement and want to realize the NOT gate using the NOR, you can check this. Again, you short the two inputs of NOR gate, you can realize the NOT gate. So what is the NOR gate? NOR gate is nothing but A plus B whole bar, right? So instead of B, I'm going to put it A. So A plus A, it becomes the A, and A bar of it's A plus A is equal to A. So you can realize the A bar. So that's what the function of NOT gate. Same way you can also define, you can also observe the function of AND using the NOR gate. So it's nothing but NOT plus OR. That terminology if you apply, and you have A bar and B bar after the NOT gate, and that A bar plus B bar of bar, you will have A dot B. That's a function, right? So again, you can realize the truth table here, and from truth table, say it's a truth table of AND gate. Same way OR, it's like NOR is like OR plus NOT. You just put one more NOT function using the NOR, you can realize the OR gate using the NOR. You can check this. This is the NOR where A plus B bar you are going to get, and that A plus B bar, then you have a function of NOT. You will have a plus B bar of bar. You will have A plus B. So that's a function of OR gate you can realize here. So from that you can see the truth table, and from truth table you can realize both the um, both the gates are having the you can realize the implementation of OR gate using NOR only, right? So this is the same terminology like NAND and NOR we are using to make the basic gate. Same way XOR logic you can also realize using the NOR. So this is what a function of XOR, where you have A and B straight away applying to NOR gate, then you have to utilize the NOT function using the NOR, and then finally you have to apply to NOR, and the whole that you can apply to NOR gate. So it's A and B you are applying to NOR gates, it becomes A dot B, sorry, A and B you are applying to NOR gate, so it becomes A plus B bar. Then you realize the NOT gate and NOR gate. See, that will give you A dot B. So my final answer would be for a XOR gate is A bar into B plus A into B bar, right? That part you can realize using the this particular truth table. So here, what we have done, we have used a NAND gate, we have used a NOR gate, and for both separately universal gates, we have implemented NOT gate, OR gate, AND gate, and XOR gate. That's why they are called the universal gate. Even somebody is going to ask, sir, can we design or can we implement the Boolean function of NOR gate using NAND? Yes, you can, right? So it's just OR plus NOT. So again, you already know how you can make the OR gate using the NAND gate, and then you just put the NOT. See, you can have a you just put the NOT and you can have a NOR gate. It's very simple, right? So once you realize the OR gate using the NAND, and you'll have A plus B, then you just put the NOT gate, you will have A plus B bar. So that's what the implementation of NOR gate using the NAND. And you can have the same thing, implementation of NAND gate using NOR, right? You can realize here truth table, and that truth table shows the uh, truth table of NOR gate. Same way here NAND gate you can utilize, same way here NAND gate you can realize using the NOR. Formula is same, you just realize the AND using the NAND, and then you put the NOT gate, right? So from that, here you can be able to implement any logic gates or any Boolean function exclusively separately with NAND and NOR. That's why these two logic gates are called the universal gates, right? You can see the truth table of NAND gate, and that exclusively based on the implementation or exclusively based on the using the NOR gate, right? So you can just see this, and you can realize that. So that's how here what we did in a summary. In summary, we what we did, we have implemented NOT gate, AND gate, OR gate, XOR gate, as well as NOR gate using the NAND, right? Same way here we have realized NOT gate, AND gate, OR gate, XOR gate, and NAND gate using only NOR gate, right? So by that way here we can understand. Thank you, dear student. Thank you very much.